So now we're going to talk about a data structure for encoding the triangulation. Okay, and if you recall, it's like when we talked about ordered triangles, there was this idea of having a particular triangle with an sort of distinguished leading edge and a particular orientation, if you will. Okay, so and we had labeled that 0, 1, 2 or and 4, 5, 6. Okay, so there's 6 possibilities. So let's consider a triangulation. K of a connected compact two-dimensional manifold without boundary. Okay, and then we can store the vertices in a linear array. Let's just denote that array by V, and it has entries 1 to n. Okay. Then the triangles are going to be represented as a graph, if you will. Well, technically the triangles are represented as nodes in the graph, right? And then, as you might expect, two nodes, it's like in the graph, are connected if the corresponding triangles share a common face. Right, so the edges in the graph, right, connect triangles, connect nodes which correspond to triangles with a common face. Okay, so if you happen to be in the situation where you have a two-manifold without boundary, which is connected, right, then what happens, of course, is that every triangle is connected to 3 other triangles. Okay. Okay, so let's look at an example of this. Okay, so let's consider this triangle here, ABC. Okay, and I'm going to label that triangle mu, and I'm going to give it the following leading edge, okay, which of course induces an orientation. And I want to sort of append the 3 adjacent triangles. Okay, so let's say we have one here. We have added the point x, okay, but it shares the points A and B, and I orient it in this way. Let's call that mu x. And then there's one where I've added y. Let's call it y. And that's mu y, and I orient it this way. And I have an additional triangle which has a new vertex z, denoted mu z, and I oriented it this way. Okay, so these leading edges tell you then it's like what corresponds to, in some sense, the reference ordering. It's like of the vertices. It's like in the previous discussion we had about ordered triangles. So the arrow, if you will, denotes the reference ordering. Okay, so mu then, right, is ordered as A, B, C. mu x starts from a, b, x, mu y, right, goes from a, y, c, and mu z is z, b, c. Okay. All right. So in addition to that, right, then we want basically two things. We want to know what is the starting vertex. Okay. So let's say that you have a triangle mu with a particular orientation I, and we look at the origin, if you will. So this contains the number corresponding to the first vertex. Okay, so and the number is of course going from 1 to n. Okay, and then the other thing it's like you want is mu I f next. Okay, which is essentially the next face, right, the adjacent face to it, and this will contain the face which is which shares the leading edge as a common subface. Okay, so this contains the sort of triangle, if you will, that has the leading edge in common. So here it's like they have, here you have two which both represent the same leading edge, right? So that's telling you that orientation 0, it's like of this particular labeling is equal to orientation, is consistent with orientation 0. It's like of this triangle. So so here, if you take mu comma 0, right, this triangle with the 0 orientation, and you take f next to it, right, this is equal to just mu x comma 0. Okay. All right. So of course, yeah. So so with that, it's like then you just create a bunch of operators. It's like which basically read these internal pointers. Okay. Okay, so this representation is in some sense redundant, right? It's clearly redundant because even if you say that, well, every particular ordering, it's like is only going to contain the adjacent triangle, it's like for which shares that common edge, right? So you would need, 3 of them, right, to represent the 3 adjacent triangles. It's like, but of course, it's like you have 6 possible permutations, so there's a redundancy there, but it just makes your life a little bit easier. It's like when you prescribe the other algorithms. So for the purposes of clarity and transparency, we're not going to, it's like worry too much about this overrepresentation, if you will, of the data, and we're just going to leave it there because in some sense it's easier to work with. Okay. So let me just sort of give you the, the things you have to do to traverse the triangulation, right? To traverse the triangulation, right? We need sort of 2 things, right? We need to return an again an ordered triangle, right? To f next, which is sort of the next face, if you will. UI, and that's only again just returning the internal data which is in the data structure. Okay, and then the same thing for the origin, right? It just returns the origin. And of course, the reason why you do this is because you don't want, it's like if you think of this as an object, you don't want it's like a piece of code to directly access the internal data it's like in that object, because that then makes it harder for you, for example, to change the representation if you decide to change the representation. Okay, so so you always want to have these prescribed ways of querying the object. Okay, so anyway, so this as I said, this representation is clearly redundant. Okay, but it improves the transparency of the implementation. Okay. All right, so let's stop here for now.